I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day, and I just pray that you bless this class. Help us to glorify you, Lord, in what we do. In your name I pray, Lord Jesus. Amen. So, guys, do you have any questions about my fascinating video lecture? Yes, Benjamin is adorable. That is true. I should do that more. Say, every new subscriber gets a new baby face or something. I don't know. But okay, so I think the thing that I should talk about next, and I try not to talk about it too long. I just want to make you aware of some of the difficulties. I want to make you aware of what's known, as well as the challenge of proving it. Okay, and so this is from Zorich, which is his Mathematical Analysis, Volume 2. So this is what we should use for calculus for math majors. Well, I mean, I think it's pretty rigorous. I don't know. I'm not the best person to ask about that sort of thing. You've heard me talk long enough, you know. But Mathematical Analysis 1 is also the size. So this is a translation of a well-known Russian calculus textbook, which is pretty beastly. It's got pretty much everything and proofs of most things. And so he has a discussion of the Fouché derivative and these things we've been doing. And so in calculus 1, what's the derivative? It's f prime of x is f of x minus f of f of x minus f of a over x minus a as x approaches a. We say that's f prime of a, right? So, but f prime of a is what? It's a number. And then we say as a ranges, we'll say a maps to f prime of a defines a function. We call that function the derivative, right? But now the derivative has been replaced with the differential, right? So at each point we're applying a linear transformation. So the thing that would have been the differential, the thing that we before had a function called the derivative, now we would have at each point we're attaching a linear transformation, right? So it's not the point-wise assignment of a number, it's the point-wise assignment of a linear transformation. It's a transformation-valued function. This is something you haven't had a lot of experience with. And so if you think about derivatives, higher derivatives, then you're basically begging the question, how do you differentiate a transformation-valued function of a point? And so, I mean, he explains it here. So, f prime, the derivative, it's going to be a mapping from u to the linear transformations from x to y, right? And then if you were to differentiate that, then that would be a mapping from this, from the from u, excuse me, it would be mapping from u to the, he calls this thing y1, linear transformations from x to y1, then you'd be mapping from u to linear transformations from x to y1, which actually is notation from, it's actually be a linear transformation that takes as input a vector and output a linear transform. I don't know, I get lost pretty fast. I mean, I'm not saying it quite right, but it's quite involved. I mean, you start getting linear transformations of linear transformations of linear transformations of linear transformations. You keep going down this path. Now, there's a fortunate isomorphism between these things. I mean, you end up not actually having to do quite this awfulness. You're able to identify the nth derivative with what's called a symmetric multilinear map. Where's that stupid thing gone to? Curses. So it turns out, and you can read this to be more careful, but after a little bit you can argue that in fact the nth derivative you can identify as an n-linear map from the domain to the range. So I mean it has to do with that. And anyway, the main theorem that you want to prove is the one we assume in calculus 2, which is that partial derivatives commute, right? And so that's actually proved in here, over here. So, it actually has the proof that the nth partial derivative commutes. I'm not going to try to explain, but if you read this couple pages, it'll give you a proof that partial derivatives commute, and then it gives an indication how you prove that higher partial derivatives commute with one another. But it's pretty technical. I mean, it's somewhat involved. And I'm mostly content to try to make sure you guys have good intuition about first derivatives. I want you to know that the theory of higher derivatives is well developed, and it's in textbooks. It's just not something I currently set up to really exposit decently. Now, I did write a fledgling paragraph on it. So there's a stub in my notes about it. This might make more sense to us anyway. So if we have f from u to w, dfa will be so u is an open subset of v. Then the differential at a is a mapping from v to w, right? So f prime would be a mapping from u to linear transformations from v to w, according to the map a maps to dfa. So in other words, f prime of a is dfa. But since this is itself a normed linear space with respect to the operator norm, we can differentiate the derivative with respect to the usual Fauché derivative because it's a mapping. I mean, after all, this is a mapping of normed linear spaces, so we can differentiate it. And so dfa prime would be from v to linear transformations from v to linear this. And we would define f prime prime like so, all right, by that. So it would be the derivative of the derivative, which is what you could expect. It's also the Fauché derivative of the derivative at a. The isomorphism I was talking about is as follows. So to trade these sorts of things, which I think are, to me, these are hard to think about. This is a linear transformation valued linear transformation. I can instead look at that as a bilinear transformation, mapping with two inputs from v and w output. There's a bijection between these things and those things. The bijection is simply this, psi of t, so t is something in here, x comma y, so I'm saying that this psi of t is something in there, which means it takes in pairs of vectors from v and outputs w vectors. Well, how do you do it? You just take t of x, right? T of x is something in here, right? And then feed y into it, that gives you a w thing.
So it's basically currying?
It's basically currying. Very good. Like the Curry-Howard correspondence?
No, that's a different thing.
Oh, curses. I was trying to sound intelligent. I really don't know what you're talking about. Sorry, you should understand, when it comes to computers and computer science terminology, I'm an idiot. Yeah?
So does that mean if you take like the 85th derivative of this, you'll have 85 inputs and one output?
Right. The 85th derivative of a function, we could either look at as this like linear transformation of linear transformations of linear transformations of linear transformations, or as a 85 linear w-valued map, n-linear map, using the isomorphism like that. And then the theorem you can prove is that it's not just an n-linear map, it's a completely symmetric n-linear map. And when you prove that it's a completely symmetric n-linear map, in other words, that the inputs can be switched, that implies that the partial derivatives commute in any order. The proof of it involves the mean value theorem, and it's a little bit subtle. It's about as hard as the chain rule that I glossed over. By the way, the complete proof of the chain rule is also in here, I think. And maybe a homework problem or two of yours. I think I saw that he has the argument for the Fauché derivative of the exponential in here. I don't know how complete his argument is, but that might be helpful for mission 2. I was personally thinking that we could take partial derivatives of the exponential and then use those to take partial derivatives, look at them, see that they're continuous, and then use that to construct the differential for the exponential in that problem. That's what I'm hoping makes sense. I still need to sit down and actually try it myself to make sure I'm not sending you down a horrible, horrible path. I mean, I have some history of assigning homework problems that are open-ended. Hey, but that's research, right? That's what I was told at the start of this semester, is we should do course-based research. So today is going to be an exercise in that, yeah? So anyway, I'm sorry I'm not giving you the full story, but I at least copied a chapter out of this wonderful book where you can read the complete and unadulterated proof of it, as well as get a sense of the next level of sophistication in what I'm doing. This is a little bit above what I'm doing. There's a little bit more attention to infinite dimensions in here. My infinite dimensional examples are mostly from here this semester. The norm on n-linear maps I got from Zorich, for example. Okay, so what I want to talk about next is something really quite different. And so I want to make, now the next, in terms of this, the next chapter is on inverse and implicit function theorems. If I get to that today, great. If I don't care. What I want to make sure I talk to you today about is the relation between this course and complex analysis. All right? So I'm going to try to do my level best to explain that, and then hopefully go beyond that and show you a little bit more about some of the things I've learned recently. So let me put this away because I don't need this. Famous last words. Let me turn the lights back on too. These glasses are driving me nuts. So has anybody in here had complex analysis already? Cooper, you're in it? You're in it? Anybody else? No? Okay. So complex analysis in a nutshell is what it is. You take calculus 1 and you replace real numbers with complex numbers. That's most of our complex analysis course, right? So to begin with, definition, f prime of z would be what? It'd be the limit as h goes to 0 of f of z plus h minus f of z divided by h. So here, let's say f is a mapping from the complex numbers to the complex numbers again, all right? We usually write, if you want to get into the details, we write f is equal to u plus iv, where I squared is minus 1, right? So this is, if this limit exists, then the function is said to be complex differentiable at z. Let me make it a z naught, just to be annoying. Okay, there we go. Yep. So this would mean f complex differentiable. I'm trying to spell differentiable. I'm having marker malfunction. Differentiable at z naught. Yeah, so I guess you got me. I guess the first question is, what do we mean by limit in complexes, right? So what does that mean? All right, back it up for a second here. What's the limit as h goes to 0 of g of x equal to L mean? G of z. Oh, I guess h. Sorry. Equal to L. If and only if for epsilon greater than 0, there exists delta greater than 0 such that 0 less than, instead of doing h, I'm sorry guys, I gotta fix this. Z goes to z naught. Let me put a z here to make it more exciting. So this is, for h epsilon greater than 0, there exists a delta greater than 0, such that 0 less than modulus of z minus z naught less than delta implies that the modulus of g of z minus L is less than epsilon. Now here are these bars, z, modulus z. What that means is the square root of zz bar, right? So typical notation, z is x plus iy, right? So this is actually the square root of x squared plus y squared. Well, it's fine, you got me. Details. I mean, it's a good question. It's just a question that comes with, that for me to answer, honestly, it takes me a lot of writing. So, right, so what I'm trying to get at here is the complex limit, right, is really the same as the Euclidean limit that we've already talked about in the plane in here, right? I mean, it's complex notation, but honestly, it's the same limit. Okay? So we can do pretty much the same calculation that I did my first example right after the definition of Fouché derivative, where I showed that the connection between the Fouché differential and the derivative with respect to a function from R to R, that same calculation goes through here. And you can basically take this and say, aha, well, if f prime of z naught exists, then the limit as h goes to 0 of f of z naught plus h minus f of z naught minus f prime of z naught times h divided by h. Fun fact, we can put a norm on that. I mean, I actually, for complex numbers, I can actually delete this, right? Division by a non-zero complex number makes sense, but if this is true for, I mean, this is true for complex numbers, okay? And if, another theorem, by the way, if we have the limit as h goes to 0 of g of h is equal to 0, that implies that, well, I don't know how to say this without a lot of, let me not belabor this point. The point is that I can do this, and the same limit is still true. The reason I want to do that is just to make the connection. I'll leave that as an exercise for you guys. There's really not much to do there. But the reason I want to say that is then this is the Fouché quotient, right? For f from R2 to R2, noting that the complex number system is R2, right? In the sense that we're making a comma b identifying as a plus ib, right? I mean, that's the notation. Are you guys with me? So if that, my little red sheet aside, what's the Fouché derivative for a complex differentiable function? df z naught of h equals to what? And by the way, the thing you guys are about to tell me is linear. What is it? Look at this. I mean, what is it? It's just that, right? Not terribly surprising. That's exactly what we found for real valued functions of a real variable. The Fouché derivative was just f prime of a times h. Same thing here. Is that linear in h? Right? I mean, it should be clear that this is linear from C to C, right? But it's more than that. It's a really, really special, which means really it's linear from R2 to R2, right? If we want to keep it real, think about it in terms of its real meaning, right? I mean, a complex function is a very special kind of function from R2 to R2. It's a function from R2 to R2, which is differentiable, and the Fouché derivative, the differential, has a very special structure, right? What is this? So the question then is, like, this structure is so special. What is this? Why is it so different than other things? Right? Let me just write this out. So let's suppose that f prime of z naught is a plus ib. Okay? And let's use the notation h is, say, h1 plus ih2, all right? Because this is a complex multiplication. And so to multiply complex, that is what? That's ah1 minus bh2 plus I, right, times bh1 plus ah2, which is what? I mean, let me, one more step here. This, in the other notation, it's this, right? Ah, math. So we can rewrite this column vector as a matrix column product. H1, H2, what's the matrix we're looking at here?
A minus B.
BA, right? But F is equal to U plus IV. In other words, it's UV like that, right? So the Jacobian matrix of F also is what? It's UX, VX, UY, VY. Right? That's the Jacobian matrix for a function from R2 to R2. Looks 2 by 2 matrix like that. And so what we're saying is that, by the way, you know, A minus B, BA is equal to UX at Z naught, apparently. Y at Z naught. This point dependence is such a drag. VX at Z naught, VY at Z naught. So what's this, you know, pattern? A is A, B is B, right? So what equations do we have? What equations do we have here? From A, we see that UX at Z naught equals to VY at Z naught, right? And from B, B equals B, right? So what does B tell us? Vx at Z naught equals to minus Uy at Z naught. So there's a theorem. Ux equals to Vy and Vx is equal to minus Uy wherever F equals to U plus IV is complex differentiable. These are called the Cauchy-Riemann equations. So once you learn these, you always want to ask the opposite question, right? Like, if the Cauchy-Riemann equations hold, does that mean that the function's complex differentiable? No. You need more. If the function is continuously differentiable, as I talked about last time, and the Cauchy-Riemann equations hold, then you get complex differentiable. But you face all that murkiness of partial derivatives existing but not pasting together nicely. So if we assume continuous differentiability and Cauchy-Riemann equation, so this is another, you know, theorem. If U and V are continuously differentiable and Ux is equal to Vy and Vy is equal to minus, I'm sorry, what did I do? Oh yeah, I'm about to write the same equation again because I'm an idiot. Vx is equal to minus Uy, right? Then F equals to U plus IV. is complex differentiable. Let's say on U. Some open subset of the complex numbers, okay? I have to use a big gun. I mean, I'm using that continuous differentiability theorem here to put things together, right? So in the complex variables course here, because we don't prove the continuous differentiability theorem on its own, and we don't assume advanced calculus is a prerequisite, most instructors who teach it are going to prove the analog of continuous differentiability theorem as it applies to complex variables, right? At which point the generality and beauty of the theorem is lost because it's all mired in complex details. But it's a general theorem, that continuous differentiability thing we did last time. So in my view, the thing that makes a complex function really complex differentiable is the fact that this differential has this very special property. Okay? So let's look at that special property for a second here. So suppose you have df z naught of h is equal to f prime of z naught times h, right? What makes this so special? How to characterize this formula? Like I mean, yes, the Cauchy-Riemann equations, right? But can we find something that's a little bit sort of more macroscopic, like a better description of it, which isn't so like stuck in the details of U and V? What is it algebraically which distinguishes this from other functions in the plane?
Function must be like this alpha such that the function is equal to alpha times h.
So you're like, I think I hear what you're saying. If I put alpha h here, right?
I kind of mean remove it alpha.
I'm going to take your comment and fashion it into what I want to hear. So the point is that complex multiplication in the argument of the differential factors out. In fact, if you have a linear transformation with this property, if I have L of ZW, all right, equal to L of Z times W for all ZW in the complex numbers, right? And L is linear. All right? Of course, we can look at L as a matrix, as a linear transformation on R2. So check this out. So this is L of, say, 1 times Z, right? Which is L of 1 times Z, if it's such a thing, right? So what's the matrix of L look like? Should be L of, should be L of E1, right? L of E2. Now here, E1 is what? 1, 0, which I'm identifying with 1. E2, 0, 1, which I'm identifying with I. Right? So, so this is really, let me rewrite this. This is L of 1, and then this is L of I, right? So what kind of matrix is this? This is L of 1, and then L of 1 times I, using that property that I can pull numbers out of it again. So if we think of L of 1 as being A plus IB, right? Which, of course, in column notation is AB, then what's A plus IB times I? Right? So this matrix is it's a very special kind of 2 by 2 matrix. It's a 2 by 2 matrix which is, in some sense, the same as multiplication by the complex number a plus ib. Many 2 by 2 matrices are not fitting this pattern. Let me give you a non-example is helpful here. So example 1, if you let f of z equal to z bar, which is x minus iy, so we have u equals to x, we have v equals to y, I'm sorry, not y, what is it? Minus y, right? So what's the Jacobian look like? What's df z naught of h? Well, that's equal to, 1, 0. I'm trying to do the partial derivatives. Ux, vx, uy, vy. What's uy? 0, right? What's vy? Minus 1, right? So I have this times h, Jumping back to the R2 notation. This is not in what's called the regular representation of the complex numbers. See, there's an isomorphism between the set of complex numbers and the set of 2 by 2 matrices of that particular form. Linear isomorphism. Actually, it's an algebra isomorphism. So like, I'm going to get too far into it. Stop. Focus here. So you can see that that function is not complex differentiable, right? Because the Jacobian matrix has the wrong shape. In contrast, you could do other things like, if you look at f of z equals to e to the z, right? Then e to the z, e to the x plus iy, we know is e to the x cosine y plus I e to the x sine y, right? And so that's my u, that's my v. So what's ux plus, I'm sorry, what's, see here. What's this equation right here say about the Fauché derivative? Check this out. This says that df z naught of h, right? It's equal to df z naught of 1 times h. What is df z naught of 1? Partial derivative in the 1 basis direction, right? Which is x coordinate. So this is partial x at z naught times h. So you can check you can check the Cauchy-Riemann equations hold for this. And so f prime of z is going to be, what is it? Well, it's ux plus ivx, actually. If the Cauchy-Riemann equations hold, and it's continuously differentiable, then the complex derivative matches simply the partial derivative with respect to x. It's beautiful. And that here is very unsurprising because this gives us ex cosine y plus I ex sine y. So surprise, surprise, we get the derivative of the exponential is the exponential. Now trust me when I tell you, if you try to prove that the derivative of the exponential is the exponential from the definition of the limit, no. You got to understand that's not that same limit you faced in Calculus 1. We're talking about a two-dimensional limit. You get e to the z naught plus h minus e to the z naught over h. When you actually flesh it out and look at the real imaginary components of it, it's quite awful what that limit is. And yet, it's easy to show with the continuous differentiability theorem and the theorem about Cauchy-Riemann equations in hand. So this, in a nutshell, is what complex analysis is about, complex differentiation. And so you notice what this means geometrically is that the Fouché derivative of a complex differentiable function amounts to multiplication by a complex number. What's that mean geometrically? It's simply a rotation and a dilation, right? And so you can prove that that means that if the derivative is non-zero, it's a conformal map. It preserves angles between tangent vectors in the domain and where it maps to. You can also prove that it's what's called a holomorphic map. There exists a power series representation for it, close to there. And then, also interestingly, you can prove that a complex differentiable map necessarily has component functions which are harmonic, meaning that they satisfy Laplace's equation. All right? Yeah.
So the reason why example 1 doesn't work is because it doesn't satisfy the theorem in the top.
Exactly, yeah, it doesn't, this has, I mean, this has ux equals to 1, which is not equal to minus 1, which is vy.
Gotcha.
It so happens the other two work. But so there's like 5 equally powerful characterizations of complex differentiable functions that they're a conformal map if it's non-zero. That, like I said, the component functions are solutions to Laplace's equation. What was the other one I just said? I already forgot. The existence of the power series representation, that it's holomorphic. I mean, eventually I mean, when I think of holomorphic, I just think that the function is really just a function of z and not of z bar. This is not holomorphic because it's a function of z bar, not z. So anyway, this is complex, and then other things. You can also define a complex integral, right? How do you define the complex integral? Integral f of z dz. You can define that over a curve. I'm not going to get into it, but you spend about the last half of complex analysis you spend studying that. And there's something fascinating happens with complex variables called Cauchy's integral formula. Cauchy's integral formula links differentiation and integration in a certain sense. And long story short, we get a theorem that says if you have a function which is complex differentiable, it's necessarily complex, it's necessarily continuously differentiable in the complex sense. And in fact, complex smooth. There are no just once complex differentiable functions. If you get one complex derivative, you get all of them, subject to some minor topological considerations. But the fine print isn't that fine here either. Anyway, I'll leave that for your complex analysis course. I just want to give you a brief introduction, try to make the connection and show you where this fits, right? Because complex numbers are R2, and so in advanced calculus, we know how to study calculus from maps from R2 to Rm to Rn, in particular R2 to R2, but complex maps are so special. Okay. Now, so that brings me to define. I'm not content to stop with complex differentiable maps. I want to talk to you about what it means to be differentiable with respect to an algebra. I hope that this somewhat detailed analysis of the complex case is enough to make what I'm about to define more reasonable. So we say A paired with star, all right, is an algebra. What's that mean? If star is basically a binary operation from A to A, so this star has the following properties. Cx plus y star z and x star cy plus z So what I'm writing down is basically just saying that this star behaves like multiplication usually behaves. That's all. You can pull real numbers out. So the C is a real number, and the X, Y, and Z are algebra elements in what I'm writing. So here. So I'm dealing with, when I say algebra, I'm actually talking about real algebra. I guess I've put the cart before the horse a little bit here. Any questions about this? So we have basically distributive properties with the multiplication. Complex numbers are like this. Complex multiplication has these properties, for example. There's more, though. I want to also, we assume, and I should have really said this first. My bad for not saying it first. We assume A is a real vector space. So an algebra is a real vector space paired with a multiplication. There are more abstract definitions of what an algebra is, but this suffices for our purpose, okay? In fact, I want a little bit more than this. I'm going to actually assume, furthermore, we're going to assume that there's 1 in A such that x star 1 sub A is equal to x is equal to 1 sub A star. In other words, there is a unity. So I'm going to assume that A is unital. It's got some number 1 in it that behaves like 1. And also this, and you guys can tell me what this is called. What's this? What? Someone here knows. Come on. Associative, right? Non-associative algebras? Unpleasant. But there's a wide class of non-associative algebras that many universities have a whole course on. They're called Lie algebras. Lie algebras are a non-associative algebra where the departure from associativity is rather mild and governed by something called the Jacobi identity. Okay? So this is what an algebra is. Let me define the next thing I actually need here is we have what I usually call R sub A. These are the, this is sometimes called the regular representation of A. So what this is going to be is T from, well, let's say T in the linear transformations on A, such that T of x star y is T of x star y. So for example, you know, D, F, Z naught was an element of the regular representation of the complex numbers. Because, well, I mean, I proved it has that property over there, basically. But almost proved it. So there's an isomorphism between A and RA, which is based on the associativity of maps. So what's the isomorphism? You can tell me, Samuel. sorry, I did it wrong. Psi of x of y equal to what?
Psi of xy.
No. How about this? It's going to be x times y. The reason I say that I'm picking on, I should really pick on, who else is taking abstract right now? Tori, King. You're not in abstract. Okay, good. I mean, I'm just kidding. I know you're not. Your homework problem
Right.
is exactly this.
Yeah, that's what I was just thinking. Like, this is what you're doing for. I almost wish that I'd seen this from Rick.
This would have been,
Trying to figure it out.
this would have been useful, yes.
Yeah.
Oh. William Wolf appears. How should I proceed? I don't know. Let's see here. I'll go on. So yeah, that defines an isomorphism. And, well, I could talk about this all day, but let me stop. The point is, there's a correspondence between these kinds of maps and algebra elements. And the correspondence is just you take the element and the map, you make a map by just multiplying by it. We sometimes call this left multiplication by x of y. So it's left multiplication map. Let me stop proving everything that there is to prove about this because it's not that interesting. And then the next thing is, and I'm just going to keep things simple in here. If you look at the paper I posted on the archive a few weeks ago, I've got a more, I do this with respect to a basis for an abstract space, vector space. Formulas are most simple, special case, which is good for, worthwhile for us, is when A is just Rn as a point set. And let's say 1, 0, 0 is the identity. It's okay. Then we can define the matrix representation of A to be simply standard matrix of T such that T is in the regular representation of A. So like the matrix representation of C was these things. Because those are the standard matrices of the regular representation maps of the complex numbers. I'm going to get to it, Travis. I'm biding my time. I promised Travis an application today, so I'm not allowed to get into too much detail about the backstory here. All right. One more example is helpful, though. So-called hyperbolic numbers. I use H. This is R plus JR. And here, J squared is equal to 1. So a typical element is A plus BJ. So this times C plus DJ, the way it works, just like complex numbers, except we have J squared as 1. So, yeah. So if T is an element of the regular representation of the hyperbolic numbers, then T of, x plus jy, it's equal to A plus bj times x plus jy for some thing. And whatever you put here has to be exactly T of 1. More to the point. So let's say that A equal to the standard matrix of T, right? Then this has to have the form T of 1, T of j. See, because here 1 is E1 and j is E2. So if I say that T1 is A plus Bj, just for the sake of giving it a label, then over here we have A plus Bj times j. And that gives me A, B. This is just B plus AJ. So I get BA. So it's the same pattern, right? But no minus. So this is the matrix representation of a hyperbolic number. It's a typical element of M sub h. I think I've said just enough about algebras to confuse you. So let me get back to my definition. Suppose we got a function from an algebra to an algebra, associative real algebra, like I was just talking about. What should it mean for this to be? Then this is differentiable with respect to A at, or I usually say is A differentiable at, P if F is Frechet differentiable at P and DFP is an element of the regular representation of A. So what that means is that DFP of, x times y is DFP of x times y. Does it make sense why I'd make that a definition given what we just did about complex numbers? So what I was trying to show you about complex numbers is the heart of complex differentiability. It's really that you can pull complex number multiplication out of the Frechet derivative. So this is the natural generalization of what we mean to differentiate with respect to a variable in an algebra. Furthermore, we define f prime of p, all right, to be dfp of 1. This is shocking. And I struggled with this for a while until finally a student told me, but you could just think of it as a number. See, because I was stuck at the start of the lecture thinking of this as a linear transformation. And so when I thought about differentiating a second time, I thought about what I told you about at the start of today. But for functions which are differentiable in an algebra, the Frechet derivative, it's not just any old linear transformation from A to A. It's a very special kind, a kind of linear transformation which uniquely corresponds to numbers in A. And so I can make this definition for the derivative as a function. So if if f is differentiable, A differentiable on U, some subset of A, right? Then f prime is a mapping from U to A again, right? Where, shockingly, f prime of P is dfp of 1 for each P and A, in U rather. And I can just as well calculate second derivatives and third derivatives and so forth and so on as functions on A. It's just like calculus 1. But what is it?
This special is writing that R is.
Say again?
The specialness is sort of letting the R is because R is an algebra and not necessarily just because R is R.
Which R are we talking about? This R?
The reals, sorry.
Oh, the reals. Yeah, because I want to study real algebras. You could study differentiation over complex algebras, which permitted a complex scalar multiplication, but that would be more limiting. On the other hand, every complex algebra is a real algebra, so I include all those. But it's true, a lot of representation theorists, you look at what they do, it's all complex because complex numbers are awesome and they might make things easier. Yeah. So, let me show you the beautiful formulas that come from this. So, suppose we're working with an a-differentiable function, all right? And let's let, you know, v1, v2, vn equal to beta form basis for A, where, for convenience, we'll say v1 is the identity on A, okay? My most beautiful theorems assume that the first thing is the identity. But we know things when that's not the case as well. But here's the thing. What is then the Fauché derivative, right, at a point P of Vj? What's that equal to? I'll get us started. This is the Fauché derivative at the point P of Vj, oh, excuse me, of 1 times Vj, right? But we're assuming that the function is a-differentiable, which means I can pull the multiplication out to the right. But you guys, I mean, I know you're new to it, but what have we learned about partial differentiation and the Fauché differential? What is the meaning of the Fauché differential acting on the first basis element? I guess I need to come up with notation. The coordinates corresponding to this basis, let's say x1, x2, you know, xn. What is dfp of 1? By definition of partial derivative on a norm linear space. We defined this to be partial f, partial x1 at P. So that times Vj. But what's this? By definition as well. Well, you're right. This is also f. True, Travis. This, I could have also said that this was f prime of P. You got me there. True. But what I'm looking for, what I was fishing for, this is partial f, partial xj at P. So what we have is that for an a-differentiable function, we have that the partial derivative in the jth direction at P, it's equal to the partial derivative in the first direction at P times Vj. These are the Cauchy-Riemann equations.